Good afternoon. Today I'll be presenting our third lab, which is focused on exploring the magnetic field of the bar magnet. In this experiment, we used the magnetometer and the bar magnet to investigate how distance affects the magnetic field. Our goal was to calculate the magnetic dipole moment of the bar magnet and to create a computational model to simulate the results. The key outcome of our experiment was determining that the magnetic dipole moment, or μmag, is approximately 3.78 AMs squared. Additionally, we used this setup to explore the relationship between the bar magnet and the system and its surroundings. The procedure began by calibrating the magnetometer using a ruler and tape. After calibration, we measured the magnetic field of the bar magnet at various distances. These measurements allowed us to calculate the distance dependence and apply both the on-axis and perpendicular axis formulas to develop our computational model. We then compared our model with the collected data to observe how accurate it was. Let's now look at the physics behind the experiment. We applied the BSR law, which helps in understanding how a moving charge generates a magnetic field. We used this principle to examine the magnetic field of the bar magnet as a function of distance. The magnetic dipole formulas were essential in calculating the field along the on-axis and perpendicular axis, and we leveraged superposition to combine these results. To make our calculation simpler, we made a couple of assumptions. First, we treat the bar magnet as a magnetic dipole. Second, we assumed that the only magnetic fields present in the environment were those of the Earth and the magnet itself. During our observations, we noticed that when the magnetometer was far from the magnetic field measured in the x direction was close to zero. As we moved closer, the x component of the field increased. This was consistent with our expectations, where proximity to the magnet directly influenced the magnitude of the measured magnetic field. Data. Now let's move on to the data we gathered. As you can see from the table and graph, we measured the magnetic field at different distances, then plotted the natural log of the magnetic field versus the natural log distance. The slope of this line, approximately negative 2.805, was used to calculate the dipole, confirming our earlier result of around 3.78 AM squared. Calculations. Here we show how we derived the magnetic dipole from the equation absolute value B bar equals K R to N. By using the slope from the line of best fit and plugging it into our calculations, we successfully computed the dipole. Computational model. Lastly, let's take a look at the computational model. We wrote a Python script to simulate the magnetic field of the bar magnet at different distances. The function used calculates the dipole moment, and we set up observation points both on-axis and perpendicular to the axis of the magnet. The arrows individually represent the magnetic field at these different observation points. Computational model continued. In this continuation of the computational model, we added more features such as visualizing the field at 45 degrees from the axis. This gives a more complete view of the magnetic field distribution. The final simulation outputs confirm our experimental data, aligning well with both the theoretical and observed results. Possible errors. Now let's discuss some possible sources of error in the experiment. First, there could have been inaccuracies when calculating the dipole moment, which would affect the results of the computational model. Second, the magnetometer itself may have introduced some errors in measurements. Lastly, there might have been other magnetic fields in the environment that we didn't account for. As a result, the experimental value of the magnetic field came out to be 6.23 times 10 to the negative 5 Teslas, while the computational model was 6.73 times 10 to the negative 6 Teslas, showing a slight difference. Finally, let's talk about how the changes to the setup might affect the experiment. If we had laid out the meter stick at an intermediate angle with respect to its magnetic field, the results would have changed because the magnetic force would have contributed differently to the magnetic field measurements. The x and y components would have varied as well. Additionally, if we repeated the experiments using two magnets left together end to end, the results would have remained similar, but the magnitude of the magnetic field would increase since the magnetic moments would align and add together. Thank you.